last step, this one. So students, it's visible?
Yes, sir.
Good, thank you very much. All right, so I remind you that we have defined a measurable space and measure on a measurable space. So one more time, X is mu will be a typical measure space where X is a non-intersect, S is a sigma algebra on X, and mu is a function from S to 0 infinity closed function which satisfies, it takes empty set to empty 0. It assigns empty set to 0, and it is countably additive in the sense if you take a sequence of disjoint measurable subsets, and then this mu acting on the union will be equals to sum of the measures. Okay, so that's the definition of a measure space. And today we follow this notation L plus, L for Levitt and plus for positive value. So it is the set of all measurable functions from X to 0 infinity closed. Okay, that's the reason I said plus, it's a positive value, and L stands for Levitt because when you say measurable, this S plays role. However, when you say it's measurable function, the measure doesn't play any direct role yet. So now we have to bring measure on the measurable function. So that we do. And told you that I told you that the simple, the characteristic function or indicator functions plays the role of building block. And here is a new another definition. So let phi belongs to L1. That means, one more time, it's a measurable function and positive, non-negative measurable function. Okay, and let phi equals to sum of alpha I chi of ai. So when you take a simple function, remember the simple function means it takes only finitely many values, right? It assumes only finitely many values and always real value. That means phi doesn't touch infinity. The range is the range of phi doesn't take infinity, is not in the range of phi. You know that. So you can typically write phi as sum of alpha I chi of ai. And remember, what is ai? Ai is the inverse image of. So ai is the inverse image of alpha I, right? And you assume alpha I not to be alpha j for I not equals to j, so that this is more neat. So this is a neat form, and this is going to be finite because it's a simple function. So is it clear that we can always write phi in this way, right? And this is what we'll write always if you have a simple function. Now, given a simple function, you are going to define the integration of the simple function with respect to the measure. So now you are in the measure space, okay? As of now, till this, you just say measurable space is fine, but here you introduce the measure. So for each E in S, that means a measurable subset, right? That's the definition of measurable subset. We define the integral of phi over E with respect to mu. So now you have a measure, okay? So this is the notation, integration of the simple function phi over E with respect to mu. E must be a measurable subset, otherwise the right hand side will not make sense. So you can see that. So by definition, this is nothing but sum of alpha I times the concentration of the measure on E, but with respect to AI. In other words, sum of alpha I mu of AI intersection I. So this is the definition of your integration of simple function. Okay. All right. So is the definition is clear? Look, I started with simple function. I want to go to the level of general function f in L plus, and then forget about 0 infinity. It should be all over extended real line, but right now at the level of simple function, non-negative simple function, and that's my definition. Okay. There is a remark, you have to be careful about this infinity Remember, this function could be infinity. Of course, phi doesn't assume infinity, but your measure can take infinity, right? Measure is a function from s to 0 infinity closed. So we know that alpha i's are in R, as I said, right? Simple function is always real. Okay, that is alpha I cannot be infinity for any I, for all of I, right? However, we may have that the sum of the measure in the right hand side may be infinity. You don't know. That is possible because mu can take infinity. So if that is infinity, in that case, and if your corresponding alpha I, suppose this is infinity for some I and the corresponding alpha I non-zero, then your sum, this right hand side and hence the left hand side, the integral could be infinity, right? So also if alpha is 0 and the measure of AI intersection in E is infinity, then we know by convention that the alpha I times measure is 0, because this is our convention, 0 times infinity is 0, right? And so this is what you have to keep in mind. And also you have to be careful that, not to be careful perhaps, because of this situation, we won't face infinity minus infinity type in this consideration. You see that? Because you are not going to get infinity minus infinity because your function is just non-negative valued. So you are not going to get infinity. So this is also non-negative. This is also non-negative. You are not going to get infinity minus infinity or infinity times minus infinity kind of situation. These are delicate things. We have not defined, for instance, what is the meaning of it, right? So you don't have to worry about this part in this case. So when we talk about integration of general function, this, that, whatnot, you have to keep this in mind, how I deal with infinity minus infinity kind of situation. Okay. Okay. So another notation. So often we write integration of phi over E with respect to mu as just simply integration of phi over E. So mu should be clear from the context. And if you want to be a bit fancy about variable, etc., then you want to write phi x d mu x over E. So these are all same notations. Okay? There is no difference. And here is a remark. Suppose you take phi to be a simple function in L plus, and you take this neat form, sum of alpha I chi ai, then phi times chi e, where E is a measurable subset. So if this and E is measurable, then the product phi times chi E is also a simple function, and it is going to be in L plus. Is clear, right? If it is not very clear, then you can rewrite this. What is the meaning of it? The meaning of phi times chi E is nothing but sum of alpha I chi of AI intersection E. I runs from 1 to n. So it's very easy to see. If you don't see right now, just take it as a little homework. Just check left hand side and right hand side. You see this to be hold. Okay. So if you take a simple function and if you multiply that with the integrator function chi e with E measurable, then the product is going to be of this form. Well, without E, it is going to be equals to this. But if you assume E is measurable, then the product is also going to be in L plus. That's the point, right? So if this equals to this, then you look at this definition, right? So integration phi d mu is alpha I measure of AI intersection E. So then you can say this is nothing but integration of phi chi E d mu over x, because here is the argument. So if you take over x, for instance, where is that? Okay, so if you take over x, if you look at the right hand side, then you take the intersection of x, but it doesn't make any sense because x is the full space, so x disappears and you get the left hand side. Right? So if you want to say phi d mu over E, you can replace E by phi times chi E, integrated E, d mu over x. And since your E is supposed to be measurable to talk about the left hand side, you are good to go. Okay, so this is a very simple simplification. Perhaps you want to use, we use on and off it, so you don't get confused. So I want to make this point, right? So any questions so far? You want me to remind you anything or something? And I hope you are not lost, right? I mean, if you are lost, you want me to remind you something, please feel free, and I'll do that. Okay, so I have a note here. So after this observation, you can say, therefore, at the level of simple functions, not beyond. Okay, we are right now at the level of simple function. At the level of simple functions, instead of talking this, we can talk about the right hand side. Do you agree? So at the level of simple function, if you want to talk about integration of phi over a measurable set, you can talk about integration of simple functions over full X itself. Clear? Because if you say left hand side, I'll straight away go to the right hand side for another simple function. That's the reason. But at the level of simple functions, so far, right? I do not know about anything beyond that. Now, a couple of useful facts. First one, okay, so we start with phi and psi from L plus. One more time, L plus is what? L plus is the set of all non-negative measurable functions on X, and at that level there is no measure mu, and we introduce the integration of simple functions so far, which requires the measure. Clear? So you take a pair of simple functions, phi and psi. Then integration over X, you see I'm doing over X in principle because, you know, this is the reason. So the same thing works for E. Anyway, so integration of alpha phi over X is equals to alpha times phi for all alpha positive, because, you know, otherwise it will be not defined, correct? Because we have defined only integration for non-negative function. And certainly alpha cannot be infinity, because if you write alpha times phi, then alpha times phi also is a simple function, right? So you cannot talk about alpha equals to infinity, otherwise you will be in difficult problem. You will be out of problem, out of the setting, correct? The proof is easy, of course. Already I said, since alpha is positive, alpha phi is also in L1, as alpha equals to infinity would imply alpha phi is won't imply alpha phi simple, so your alpha is not equals to infinity is needed, and alpha phi is another simple function which you rewrite it in this way, and that solves the problem. So that proves the equality, correct? It's very simple. Second property is the following. Second property talks about two things. It is the following. So you start with phi and psi, simple functions, and you take a scalar again, alpha positive and not equals to infinity. Then it says alpha phi plus psi is also integrable. The left hand side, the meaning of the left hand side is that alpha phi plus psi is also integrable, number one. And then you say the value of the integration is equals to the right hand side, that alpha times integration of phi plus integration of psi. Okay, so there are two parts. First of all, existence of the existence or in the sense of integrability of the sum, and the value of the integration, correct? Now if you see this carefully, then this equality tells you that the integration is a linear function on the space of non-negative simple functions, right? We are at the level of non-negative simple function. At that level, the integration is linear. This is what it says. Clear? So I am saying that in view of number one, which you proved already, that we can assume that alpha to be 1, because if you can prove this, you know, keeping alpha inside, then use 1, you can take it out. So alpha is 1, then I have to prove integration phi plus psi equals to integration of phi plus integration of psi, right? As usual, we take the neat form of phi and psi. So phi equals to sum of alpha I chi of ai, and psi equals to sum of beta j chi of bj. As usual, alpha i's, beta j's are distinct. Now, when you write that, you know, this is equality, right? So you are assuring that the AIs are disjoint subsets, and the union will give you X, correct? This is the part of the construction. So when you write this, you assures that your AI's union of AI's is going to be full of X, correct? So your AI's disjoint union of AI's and disjoint union of BJ's are all of X, and that tells you, since it's all of X, for fixed I, all AI, for each I, you can rewrite AI as disjoint union of AI intersection BK, K from 1 to L. You see that? I'm just using this because I'm hitting AI with X. If you hit AI with X, the right hand side will be that, and the left hand side will be AI. Similarly, BJ is also disjoint union of AK intersection BJ, where K runs from 1 to N. Here, K runs from 1 to N, right? I want to prove this, by the way. I'm doing this little carefully because you get more confident about this idea. If that is the case, then the measure of AI, since it is disjoint union, remember the property, and these are all measurable subsets, right? Because AI measurable, BK is measurable, so intersection is measurable, right? So the measure is going to be the sum of the measure of this guy, and subsequently measure of BJ is going to be sum of the measure of these guys, right? So this is what I have. Once you are in this situation, you can therefore write integration of phi x, which is by definition alpha I mu AI, and I runs from 1 to N. Then you can write mu AI using this equality as sum of alpha I mu of AI intersection BK. Now your K will run from 1 to N. That's okay. And this is what you get. Similarly, you get integration of psi as integration of beta j measure of AK intersection BJ. Wonderful. You get all of them. AI intersection BJ, right? You get all of them. So this is your phi and this is your mu psi. The right hand side are new, right? So once you have this, you add it up. So integration of phi plus integration of psi will be, they lives everywhere. AI intersection BJ, no problem. And you pick up alpha I plus beta j times the measure AI intersection BJ. Clear? And that's the definition of your integration of phi plus psi. Why? Because your phi plus psi, as you have rewritten, as as you have done this. Where is the phi and psi? Right here. So if you look at this, and if you where is that? I have not written this part, but it is perhaps very, very evident that if you rewrite, you can rewrite your phi plus psi as sum of alpha I plus beta j times. That's bit of wrong, right? What should I write here? It's chi, right? So I don't want that. So this is chi. This is the indicator function. Chi AI intersection BJ. Right? Do you see that? So if your AI is this, BJ is this, which using this you have rewritten mu of AI, mu of BJ. That's fine, but with this AI and BJ, since your phi is sum of alpha I, since your phi is sum of alpha I chi AI, and so you can rewrite chi of AI as chi of AI intersection beta BK, and similarly that. So it is now you can align them and you can rewrite the sum as phi plus psi as sum of alpha I plus beta j times chi of AI intersection BJ. So are you convinced this is fine?
Sir.
Thank you. Oh, you have a question? You said yes.
No, sir.
Okay.
No, sir.
Good. Thank you. Fine. So we understand that this is a linear function. Integration is a linear operation function, or whatever, I don't know, whichever you want to say. Linear operation at the level of simple, non-negative simple functions, measurable functions. Third property is also very useful. It is monotonicity. That means if your phi is less than equals to psi, then the value of integration of phi is also going to be less than equals to psi. Okay, so it's another useful property. So as above, we are going to use the same representation. So this is what I didn't write. I think officially I didn't write phi equals to that, right? I think I missed that. Yeah, but it is here. So you can copy from there, no problem. So you can rewrite phi as sum of alpha I chi of ai intersection bj. Subsequently, you can rewrite psi as beta j in chi of ai intersection bj. It's kind of same coordinate, okay, like that. And you are saying this is less than equals to psi, it's given, correct? Now, evidently, it is not guaranteed that you are going to get ai intersection bj is always non-empty. But if it is non-empty, if it is empty, the coordinate is very easy. It's going to be 0 either way. But if it is non-empty, then your phi restricted to ai intersection bj is going to be alpha I, right? And then subsequently will be also beta j, right? And the beta j is going to be psi restricted ai intersection bj, and by assumption your phi is less than equals to psi, so the restriction will also maintain that, and that going to say that your alpha is less than equals to beta j whenever it is non-empty. If it is empty, then there is no comparison. I mean, it's all 0, it's gone. So once you have this, then you can again write integration of phi as sum of alpha I, measure of ai intersection beta bj, and subsequently you can say, you can replace this alpha I with beta j at this level, and then you maintain the inequality, and the right hand side is going to be your integration of psi, and that proves the result. And if there is any empty case, you don't have to count because it's 0, it's gone. Okay, so it's linear number. Yes.
Hello, sir.
Yes.
Sir, here what we are defining phi and psi both are simple function.
Yes.
So, sir, we can prove other method.
What's that?
Sir, we can prove other method from this.
You can prove. Oh, can we prove it other method or not? That is that what you are asking?
Yes, sir.
Possible.
Yes, sir.
Yeah, it's not deep. Possible. You have something simpler in mind? I mean, this is very simple. That's what I mean. This is very simple.
Because of, sir, I am thinking about that because of phi and psi is simple function, and given phi is less than or equal to psi, and we are proving above sum of two simple function is again a simple function. That means phi minus psi is also simple function.
You are right. That's I think you are right, and maybe I read that because that's also simple. So you said phi psi minus phi is positive, right? And then you have to prove yeah, we know that. I mean, this is linear combination, so this is also simple. This is also going to be measurable, right? So this is simple. And then by definition, so you have to write that by definition, if I am running out of notation, phi psi, let's say eta, if eta in L1 simple and eta is positive, then integration of eta over x is positive, right? Because the right hand side is going to be sum of positive numbers, is it not? And from here you can say that therefore integration psi minus phi is positive, and using the linearity and changing the side, you are absolutely right. This is much easier, but I think I felt a little guilty because I didn't, I already pointed out, I didn't write this expression on earlier proof. Perhaps it was in my rough notebook or something, and that's another reason I have done this. But you are right. This proof is perfect. Okay. Yeah, this is a better. Okay, and number 4. Suppose A is subset of B, then the integration of phi over A is less than equals to integration of phi over b. That means the monotonic, the nested property, if you want to say, is it can be kept, can be also transferred to integration. So in this sense also it is monotone. And man, I think this is, I think this is easier, because when you say phi over a, integration of phi over a, remember it is as same as saying that integration of phi of chi a, right, over x. The right hand side is the integration of phi over chi b over x. So if this is this is less than equals to this, there is 4 follows from part 3. Okay. All right. Any question? No. Number 5, this is another simple property, that suppose your phi vanish on all over E, and E is of course measurable set. If that is the case, then the integration of phi over E is going to be 0. So this is very natural. So if your function vanish on the set you are integrating, then the integration value should be the same. It should be also 0. That's the case. And even if the measure of the set E is infinity, it can be possible that your measure is infinity, but phi vanish, then still the integration is 0. It's simple, because you just have to use that 0 times infinity is 0 by assumption. So it follows from the definition, correct? Because when you write the simple function, all alpha i's are 0, is it not? Because phi is 0, so all alpha i's are 0, and hence the right the definition of integration of phi over E, the right hand side is going to be also 0. Similar reasoning also works if the measure of the set is 0, where E is of course measurable, then the integration of phi over E is also 0, even if your phi takes all the way infinity. The same reasoning. So your measure of the set is 0 means any subset you take, that measure will be also 0. So the definition, the right hand side of the definition is going to be 0. So this is a simple property. What you want to think about, perhaps not in this series of lecture, maybe next series of lecture when Sachi takes over or afterwards, you have to ask this question in other setting. Okay. So when you talk about general integration, you want to ask the same question. Maybe it will be easier. Maybe sometime it is not absolutely true, or so on and so forth. But you have to ask these questions and get the answers. Okay. So I'm just preparing the stage of future questions. Finally, one very curious observation, and this curious observation, what I call curious observation, of course, for Rudin, will be very useful when you go to forthcoming lectures. And today also, I'm going to use this equality in one of the results in these slides. It is the following: suppose phi is a I should say phi is a simple function also. Suppose phi in L plus and simple, because I'm in the level of simple function and simple. So this is given, and then you define a function mu sub phi. Phi is given, okay? Mu sub phi E as integration of phi d mu over E. Since phi is simple, the right hand side makes sense. Since E is measurable, also this makes sense, correct? So you are defining, given this, you are defining a function mu phi from S to possibly 0 infinity, no problem, by this way. So do you understand the definition? So I'm defining a set function mu sub phi from S to 0 infinity by mu sub phi at E, where E is a subset of X, measurable subset, by integration of phi d mu over E itself. Or if you want, integration over X, but the integrand is phi times chi of E. That is also fine. This is how you define. Okay. So apparently it's a function. So it's a function from S to 0 infinity. The point is that this is a measure on X, which is very useful, which is very interesting. Okay. And this is what I say, new from old. And so that means what you are doing, you are starting with a measure on a measurable space. And then what you are doing, you are picking a L plus simple function. That means a non-negative measurable simple function. From there, you are coming up with a new measure, new sub phi. So how many are there? As many phi as you have, right? So you are having plenty of measures on the same space. That's what it says. And this preparation is very interesting. New phi at E is integration of phi over E. Okay. Proof is not hard, which we will do, but keep this spirit in mind because this is going to be very, very useful. All right. So how you prove it? So you have to prove this is a measure, is it not? So to prove something, a set function measure, you have to check two properties. Empty set is 0, empty set goes to 0, and this additivity property, countable additivity, right? These are the two things you have to prove. So again, you start with a neat form, phi equals to alpha I chi of ai. Clearly, mu phi, by definition, at the acting on the empty set, phi, this is my notation, is going to be phi d mu over empty set. So according to the definition, this is sum of alpha I mu of what? Ai intersection empty, right? So in principle, you should write this phi as ai intersection empty, which is empty. So this should be ai by definition, right? And that's nothing but your empty set. And the measure of the empty set is 0, so you are done. So measure of the empty set is 0. First condition is checked. Now the second condition. For the second condition, pick EM disjoint sequence of subsets. Okay. And you want to prove that the measure acting on the union is going to add up, right? So given this, you set up E as the disjoint union of your EMs. And you know this is going to be in S because this is a sigma algebra, right? Okay. Once you are here, then you go ahead and write what is the measure of E. So mu phi of E by definition, right? By definition, it is going to be integration of phi over E, right? All right. Again, by definition of integration, this is nothing but sum of alpha I, because phi looks like this, sum of alpha I mu of ai intersection E. Fantastic. So this is up to the definition. Now you look at this chap, and for each I, the same trick. You rewrite ai intersection E as disjoint union of, now it is going to be disjoint, right? So ai intersection E is going to be disjoint union of ai intersection EM. Yeah? Once you are here, then you say by countable additivity of measures, the measure of the left hand side is going to be sum of the measure of the right hand side, right? So mu of ai intersection E is going to be the sum of these, right? Therefore, your sum, this form, takes alpha I y to 1 to n and m equals to 1 to infinity, measure of ai intersection EM, right? This is a finite sum, don't forget. So I switch it. So I take this infinity outside and take the finite sum inside, and then I relook this finite sum. That's nothing but integration of phi over EM, is it not? This is the integration of phi over EM by definition, right? So you get m equals to 1 to infinity, integration phi over EM d mu. And that's precisely your definition of mu phi of EM, and that proves the countable additivity, and that says mu phi is a measure on X, right? So any question? So just keep this in mind. This is what I call new from old. You have a measure mu given, you pick a function from L plus, simple, and then you come up with a new measure. And I hope you will see this feature in more general situation in this series of lectures, okay? All right, so now it's time to talk about integration of more general functions. Now here we are. So far, integration was defined for simple, positive, simple, measurable function. See, measurable is always there, otherwise you just can't do anything. Now, here is the next step. So f is in L plus, and if I'm not assuming it is simple. So f is in L plus, that is f from x to 0 infinity is a measurable function, and it is always there, included infinity. The Levitt integration of f over e is defined by integration of f d mu. Now, you want to do this for general function, right? You want to make sense of this guy. What you do, you keep this in the picture. So you, instead of f d mu, you don't know how to do that. You are actually going to define, but you know how to do it for simple function. Okay, do that. So you integrate phi of d mu. You integrate phi over e instead, where phi is non-negative function dominated by f, and you say phi is simple, so that this integration is well defined. So instead of, you want to define this, you don't know how to do that perhaps. So you do the following: you take all simple functions from 0 to f, and tell the 0 means non-negative, and then you say it's simple, and then you can integrate. So do that, and then take the supremum. That's the definition of your integration of f over e. The definition is clear. Okay. Now here is a little remark which I will return in after 1 or 2 slides. As of now, computing integration of f over e is difficult. See, if you look at this definition, and if you give me a function f, I mean, how you do that? Look, this is not a simple recipe. What are you saying? You have to take the supremum, which is okay, fine. I can take supremum of some number, but look at the numbers. It's a gigantic set, right? I mean, it's just any phi which is dominated by f. You integrate, right? You understand? It's not easy to compute, correct? So as of now, this is difficult as the right-hand side is soup of a large set. That's the point. So we need a recipe, and we'll talk about that. Okay, so I'll return to this. So just keep this in mind. This is a definition, but if you ask computation, it's a bit shaky. Okay, so we need something more. We need tools. A remark: suppose f is in L plus simple. So look at this definition, by the way. I have said f in L plus, you define in this way. Now, if in particular f is also simple, then you have already definition, right? If f is simple, the definition just we had it in the first line today, right? Now the question is it going to be equal to that definition? Otherwise, it's a bit confusing. So your new definition, when restricted to simple function, should match up with the existing definition of integration of simple functions. Clear? We need that, otherwise it doesn't make sense. So suppose f is simple, then it's actually fine. Then by the fact that integration of phi over d mu is less than equals to psi over d mu for all simple phi and psi, it follows that the above definition agrees with the definition of integrations of simple function with the definition of integrations of simple function. So is it clear? Right? So if your f itself is a simple function, you keep it over here, then you use the monotonicity property, right? So integration of phi will be less than equals to integration of f, because f is simple in this case, correct? So the supremum is going to be that guy. Is it right? Right. Because that chap itself lives in your set, right? So this guy itself lives in your set. So you're going to get this definition set. Okay. So we are good to go. Our definition is consistent with our existing definition of integration of non-negative, measurable, simple functions. here is a pair of remarks which you are going to use quite frequently. Suppose f and g in L plus, the same thing. Suppose f less than equals to g. So you have a pair of functions in L plus, which is one is less than equals to the other. Then the integration is also less than equals to the other, right? We proved it for the simple functions. All I'm saying, it works at the level of L plus as well. Okay. And this is very useful because you're going to use on and off. So keep this in mind. Proof you can perhaps imagine right here, right away. So if you think about the definition of integration of f over e. So it's a supremum of integration of phi where phi is dominated by f. Correct? Okay. So you take a phi dominated by f where phi in L plus simple and measure. Okay, measurable is here. L plus means measure. So phi less than equals to f. So if phi less than equals to f, then phi also less than equals to g, right? Because f is less than equals to g, correct? That tells you that if you look at the supremum of all such phi, where phi is dominated by f, integration of this guy, by the simple function inequality, preservance, you are going to get this set is going to be a subset of the integration of psi, where psi is also dominated by g. Do you see that? Correct? Whoever is dominated by f is also dominated by g, and hence this is subset. Well, if this is subset, then you can take the supremum. Actually, I did something earlier. So you can take supremum, and the supremum is also going to be preserved, and that would tell you the integration of f is less than equals to the integration of g. Okay. Now, what about using? So this is what it proves. But what about proving that using that technique? CF is larger equals to g. Can you do that? So f minus g larger than equals to 0. You can play the same game here also, right? You can play the same game. So you can take f minus g. Well, I'm pretty sure you can do, but do it. You can do it. So just check whether this same method implies integration of f less than equals to integration of g. Did I get it wrong? Who is larger than who? G is larger than, so this is g minus f. It will work. It will work, perhaps. It should, right? I guess it will work. Similarly, anyway, we have this inequality. Similarly, if you take alpha, which is not infinity, then also integration of alpha f is going to be integration of alpha times integration of f. Do I need alpha to be a real number, or infinity is also fine? For us, not needed. It will not be needed for our consideration. I think alpha is needed to be. Look, even alpha is infinity. Are you sure that we can write alpha as limit of alpha n? Correct. Suppose alpha is infinity, you can write that infinity as a limit of large numbers, right? From that point of view, I think you can do it for alpha equals to infinity as well. But I think we don't need that. But I'm just telling you how you want to think about or do it.
Hello, sir.
Yes, sir.
Sir, if we are supposing alpha is equal to infinity.
Alpha equals to infinity, yes.
Infinity. And here we get integration of f equal to 0. That means this will be a 0 into infinity. So how we will define?
Yeah, as I said, I'm not very sure. All I said that perhaps you can think about, alpha infinity you cannot do, right? But alpha n, where alpha n's are real, There you can do, right? But still there is a problem, because when you take the limit, you need something, a result which you are able to do it perhaps now. So it's not very clear. So perhaps as of now, I don't have alpha, I don't have the possibility of alpha to be infinite as of now. That's why I have not considered this is closed. Okay.
Okay, sir. Thank you.
Yeah, I'm not saying it is clear. All I said, you can think, but even you think, you will have alpha n here, right? You will have alpha n f, and you will have alpha n integration, correct? Then you can perhaps say that, see, yeah, I think this is a very standard problem in major theory, playing with infinity. Okay, it's not clear. So if alpha is infinity, the right hand side is going to be infinity, because this is a positive valued number, or it could be also infinity. That's okay. Infinity times infinity is fine. So let's not think about right now. I think I see an argument, but that requires the theorem which we are going to talk about. So I don't, right? Okay, so now we are in a position to talk about one of the most remarkable convergence theorems. Okay, this is really one of the most remarkable, and perhaps the key of many results. Of I think most of the results, one way or other. I mean, you use something which also uses this result. So it's all about passing the limit. So limit of n goes to infinity of integration equals to integration of limit. That's a simple thing which we started in day one, pointing out that this is going to be an issue, passing the limit under the sign of integration, correct? So here is the statement. Statement is very simple. You want to understand. So this is known as Levitt monotone convergence theorem, and it says, suppose you have a sequence fn in L plus non-negative measurable functions, okay, and suppose fn is less than equals to increasing. So when you say fn less than equals to fn plus 1, that means pointwise this inequality. So this is true for every x and for also for every n. So this is monotonically increasing, and you assume that limit of n goes to infinity fn equals to n. See, when I say that, this is just the notation. You already know that limit of fn, if you are in the increasing situation, since your range is containing 0 infinity, this limit is going to exist, correct? We know that, right? And also, I think if you recall in the last lecture, we proved that in this case, the limit function f is going to be measurable. You remember? Right? Sup or lim sup, these are all measurable functions of a sequence, right? So in this case, since it is going to be increasing, etc., we already know this is, so this is just not kind of assumption, it's a notation, right? So by saying this, what you are saying that limit of fnx is equals to fx for all x. So this is the definition of your fx. Then now the conclusion. Then, so essential assumption is this, is increasing. Then f is in L plus, number one. And so L plus means what? One more time, f is non-negative measurable function, right? Non-negative measurable function on x, right? Yeah, did you ask something? Any question? I heard some noise, I'm not sure it's from my outside or from you guys. Okay, perhaps not. So that's number one. And the second assumption is when you say it is, in L plus, then you can talk about this guy. Otherwise, you cannot. So you can talk about integration of f over x, and that's nothing but limit of n goes to infinity fn. So this essentially says integration of limit of fn equals to limit of integration of fn. Exactly, that's what I pointed. And this is all about Levitt's MCT, what we call monotone convergence theorem. Right? So statement is clear. Yeah. Any question? Well, you can hear some whispering. Okay. So if not, then I go to the proof, and here it is. So we know, we just pointed out, you remember, here we have done this. So we know Fn less than equals to Fn plus 1 would imply integration of Fn is less than equals to integration of Fn plus 1. That tells you, so these are all real number, possibly infinity. That's there. Okay. So this implies integration of Fn is increasing sequence, and therefore there is a number alpha, possibly infinity, such that alpha is the limit of Fn, integration of Fn. Right? So this is your alpha. What is alpha? Alpha is the limit of integration of Fn. So that's your alpha. This is your alpha, correct? All you are saying, my alpha exists, the right hand side exists. That's the notation of that I denote by alpha. And I want to prove that alpha is integration of it. That's the goal, correct? Okay. Since limit of Fnx equals to Fx for all x by definition, we know that F in R plus, as I said already. So recall, given Gn, so this we did last lecture. So given a sequence of measurable function, we know the lim, sup, lim, inf, supremum, infimum, all these are measurable. So we know this thing. We know this. There is nothing new here, correct? So we already know that this limit guy is going to be in R plus. Fantastic. Because limit exists, so limit will be in the R plus. Otherwise, you have to talk about lim, sup, inf, and all that. You don't have to do that. It's just a straight away limit. Also, Fnx is increasing for all x, or you can say, this can be said simply that Fn is increasing, right? Because we are always talking about point-wise thing. So Fn is increasing. So this is what you are saying, essentially, correct? Since this is increasing, you can, in particular, you can say Fn is less than equals to F. So Fn is going to be less than equals to the limit function. Number one, again, using the previous observation, you can say, in particular, then, that integration of Fn is less than equals to integration of F for all n. Wonderful. And this is going to be a real number. I mean, real number in the sense extended real number in 0 infinity. And then you can talk about the limit here. And since this is true for every n, this limit function is also going to be less than equals to the integration of f, right? So what you have your alpha, which is the right hand side, is less than equals to integration of f. So this is what you have very easy, without any difficulty. That's the point, without any difficulty. So this is always true, rather, right? Very easy. Hardly there is any machine. It's just increasing is all you need. Claim. So claim is the other inequality. So other inequality is what? You have to prove that alpha is larger than or equals to integration of f over x. What is alpha? Alpha is limit of n goes to infinity fn by definition, right? Here is my alpha. So you want to prove alpha is larger than or equals to integration of f. To do that, I remind you what is the meaning of integration of f. The integration of f is nothing but sup of integration of simple function phi, which is in L1 and dominated by f. Is there a 0 missing? Oh, right. L1 means not negative, right? So I don't have to write. So this is my definition. So, and I have to prove this is larger than or equals to this supremum. This is what I have to do, correct? To do that, well, I pick a candidate from the set. So I pick phi, which is dominated by f, which is simple. And L1 means non-negative and measurable. So I take that one and a representative from the right hand side. Then I do a small trick. I consider C a positive number but smaller than 1. And then I construct En as those x from capital X. I'm over X, right? And where is this? Over X. Okay. So I pick X from capital X such that Fnx is larger than or equals to C times phi x. Okay. Remember, my phi less than or equals to f is fixed. Okay. Based on that, I consider those elements from x such that Fnx is larger than or equals to C phi x. For all n, I define this. Right. Remember, I pointed out a simple, not so well, a homework. which says if you have a pair of measurable functions, f and g, then wherever, for those points where f is larger than or equals to g is going to be measurable. Remember that. So it's in our previous set of homework, right? So if you use that, then this En is a measurable space. Why? Measurable subset. Why? Because Fn is measurable, given. Phi is simple measurable by assumption, right? And C times phi is also going to be measurable. So this pair, this is a pair of measurable functions, and hence, using that homework, your En is a measurable set, right? So En is a measurable set. Look at the definition one more time. N doesn't depend on the right hand side. So since your Fn is increasing, it's clear that your ENs are also increasing, right? So if you have an x such that Fnx is larger than C phi x, then Fn plus 1x is larger than this, and hence larger than this. So you are going to get an increasing sequence of measurable subsets. Finally, you see or you claim that this gives you the union of these ENs gives you your all of x. Why? Suppose you pick something, certain it is a subset, so you pick a little x from big X and assume fx is 0. Well, if your fx is 0, if your fx is 0, then phi is non-negative function, then phi x is also 0, right? If phi x is 0, then C phi x is 0. Yeah. A doubt? No? So if fx is 0, phi x is 0, well, then C phi x is also 0. There is no doubt of infinity, etc. Even I think that's also okay. So C phi x is 0, and that tells you x lives at the level of E1 itself. Correct? So x is in E1. That proves the result. Why have written fnx is positive? Oh yeah, fnx is positive that you want to use. Yeah, because if it is 0, fnx is positive, that tells you f1x is also larger than or equals to 0. Fantastic. Now you assume fx is non-zero. If x0 is done, fx non-zero, what happens? So if fx is non-zero, then it is positive because it's non-negative function. So your C phi x is less than fx, right? If fx is positive, you apply this, then your so phi x is less than or equals to fx by assumption, right? Phi x is less than or equals to fx. So phi x is less than fx, less than or equals to fx, but then you are scaling with a fraction, or sorry, not fraction, you are scaling with a number, positive number, which is less than 1. So that would make this as a strict inequality even smaller, right? So C phi x is less than fx. Therefore, your fx is equals to limit, by definition, fx is limit of fnx. Correct? And that's going to be larger than C of phi x. So this fx, which is limit, is larger than C phi x. This is what you have here. I'm just rewriting. And if that is the case, you are going to find a natural number m such that one natural number m, let's say, such that fmx is larger than or equals to C phi x. Otherwise, how it is possible? Right? So you're going to find one m such that this inequality holds, and that tells you if fmx is larger than or equals to C phi x, that tells you that guy x lives in E sub m, right? That guy lives in E sub m. So x is in E sub m, and that proves that EM is a cover of all of x. Correct? So this proves the claim. So one more time, what you have, we have an increasing sequence of measurable set which covers x. And now we are in a little bit known territory. So what we have, by the way, what you have to prove one more time, we have to prove this inequality. That means limit of fn is larger than or equals to fx. And to do that, we started with a phi, which is from this set. And from out of that phi, we constructed En, increasing sequence, cover all of x. Fine. So clearly, since your x contains En, so integration of fn over x is going to be larger than or equals to integration of fn over En because of this, right? And integration of fn over En, if you look at over En, at En, your Fnx dominates Cpx, right? So Fnx dominates Cp, so you dominate it by Cp. Wonderful. So at least one N goes, right? And here you get En, but you get Cp, right? So that's the argument. So what you have integration of Fn is larger than equals to integration, sorry, C times. Now here the C, what is C? C is okay, fantastic. C is a real number, positive real number, including 0 and 1. Okay, fantastic. So I can take that out. So integration of Fn is larger than equals to C times phi over En for all n. Correct? Now I remind you, this is also what we have, this is what you have done today itself, that if you have a function phi, then mu sub phi defines a measure, right? So mu sub phi defines a measure on x. So mu sub phi at E is the integration of phi d mu. This defines a measure, and if this defines a measure, then what happens? Then you realize the right hand side is nothing but the measure of En, right? That's your right hand side. Clear? And then you realize, all right, since I know union of En is all of x, mu of phi of union of En is going to be mu of phi of x, and that's going to be integration of phi dx, phi of over x. That's your left hand side, correct? And since it is increasing, remember we did this in the last lecture. Since you have an increasing sequence, then this is I said this is in page 19, so I think this we did in the last lecture, last day. C3, so that's the equality part of 3. This is going to be the limit of mu of phi of En, right? And mu of phi of En is what? Well, that's, we know, integration of phi of over En, correct? So all you are saying that integration of over here, so integration of limit of Fn over x. Now what the heck, how I get this? The start, okay, right here. So the start tells you integration of Fn over x is larger than equals to C times this chap, right? And the limit of this chap, is what? The limit of this chap is the integration of phi over x. So you take the limit on both sides, if you wish, maybe a little carefully, one by one. Then you get limit n goes to infinity of Fn over x is going to be larger than equals to integration of phi over x times C. Okay, is it clear? This one. You can do it slowly. You do take the limit in the left first, and then you take the limit on the right, or one or other. Okay. Anyways, so you are in this level, and then you realize that all you have done for all C in between 0 and 1, and in particular, you can take the supremum of this C, and then the C goes away, and you get 1 here, right? And then you realize that the limit of Fn is also larger than equals to integration of phi, as you have taken the supremum over C on the 0, 1. And this is true for all phi simple such that phi dominated by F, and that's where you conclude that your alpha is indeed larger than equals to the supremum of this set, which is your Fx, integration of F over x. And that concludes the proof of the giant result called monotone convergence theorem. And here is a list of questions I have set up, and I'm sure you will get a lot of help from the tutorial. Try to do them. Some of these are relevant from today's lecture. I'm done. I'm sorry I have taken 3-4 minutes extra. So if you have any question, thank you.